In this video we're going to have a look at how we check logical conditions using Haskell. You can see here I've got a very straightforward function that returns a string based on whether the input of a character matches some pattern. So if it's an A, we return the car as A. If it's Z, we return the car as Z. If not, we return car as not A or Z. Now this is fairly straightforward and imperative. You just list out your conditions as you go. And indeed we can do the same thing in Haskell. So let's have a look at how we would do that. So we need the name of the function and its type. In this case we're taking a character in as output and we're returning a string. So this should be car to string. So far so good. Now we need a variable to work with. So let's say we get a character A and then we want to do something. Now of course in Haskell we do have if statements, so let's do it using if statements the first time round. This will be quite an ugly way to do things. We do use if statements in Haskell. They tend to come up more in do notation and input-output. We have cleaner ways of managing logical predicates. But you're welcome to use them. I would suggest that you try not to use them as much as you would normally in an imperative language and try and get used to the tools that Haskell has to offer you. But let's see how we would use an if statement first. Now, in an if statement, we need an if. So that's a good start. So let's say if x equals, and should be A, then we return the car is A. So far so good. Now in an if statement in Haskell we need to also supply the else condition. We can't just do an if then, we need to do an if then else. We need every part and every part has to resolve to the correct type. In this case it has to resolve to the return type, which is string. So then I'll need to do my else condition. But I still need to check if the character is Z, so what I'll need to do in here is another if statement, and I'll need to say if x is equal to Z, then the car is Z. So far so good. And then we need our else, and this is just the final condition, the final else in that imperative example where we just say the car is not A or Z, and that's us done. Now, this looks horrible, and you can imagine if this had a lot more conditions in it, this would be unreadable. It's already quite difficult to read this. You could use indenting to try and make it a little bit cleaner, but we're at the style of XL if statements, which is not somewhere we ever want to be when we're using a grown-up programming language. And in fact, I'm getting an error warning here, which is going to be what we're going to be introduced to next, which is guard statements. So Visual Studio Code will try and suggest the tools in Haskell that can be used to solve the problem that you're tackling, but I'm just going to go ahead and do it myself. So first I'll need to give another function name, and we'll call this checkCar1. It will also take a character and it will also return a string because it's going to do exactly the same thing. So let's do one takes an x, and now we have an equal sign. So what I can do is I could write the if statement out. I don't want to do that. I want to use something which is called a guard. Now a guard is something that takes one logical condition and specifies the behavior that should happen if that condition is met. So it's kind of similar to the little bracket in an if statement. If the predicate is met, you do something. The thing with a guard is you don't necessarily need an else condition, and you can specify as many as you want in a very clean way. So what does this look like in Haskell? Well, the reserved notation for a guard is this vertical line here. And what this means is we need to give a little condition in this spot here, and then we need to specify the behavior. So in here, I could put x equals A, and that's my logical condition. Now if that condition is met, Haskell will carry out the behavior in this line, which is specified with an equal sign. So now I just put the car is A, and we're happy. So that's what a guard is in Haskell, and we can carry on doing these. So let's put in our next one, and that would be x equals Z, and then we say the car is Z, and that's pretty good. Now one thing that's special about guards is they have another keyword that they work with, which is the otherwise condition. That's kind of like your else statement or else condition in if, where you just say otherwise, meaning if the previous behavior is not met, then do this. So we put otherwise, and we say equals the car is not A or Z. Now you can see that I would argue that this is a much cleaner representation of this logic up here. It's much easier to tease this out because you just say, okay, here's the condition, here's the behavior, here's the next condition, here's the behavior, and then here is the final catch-all behavior. Usually the otherwise should come at the bottom to make sure that you catch all of the others. As we saw in the previous video, Haskell executes on a case-by-case basis, so your otherwise should be last. The one thing that's nice about guards as well is I could easily just put another guard in here with another condition and have as many as I need. If I did this with an if and else, I would have to put another if then else and chain that logic through, which would be much uglier than this. So this is one way that we can check for this behavior in Haskell. Another way is to use pattern matching on the input to see to do the logic for us, and that's another very clean and very efficient way to do things in Haskell. Sometimes you'll want to use pattern matching, sometimes you'll want to use guards, but let's have a look at how we would use the pattern matching equivalent. And of course this is going to be the same type because these functions are all doing the same thing. And the difference with pattern matching, we saw a very brief glimpse of it in the first video where we just saw that you can match on the input of the integer for the sum up to n function. And I can do exactly the same thing here. Now these are still very simple cases of pattern matching. You'll see when we get onto lists and stuff, you can do much more stuff with pattern matching. But I can just say, if I get an A, then just do this. If we can manage our spacing. So I can just tell Haskell, if this is the input, do this, and that's about it. And then I can do the same thing for the next condition, which will be the Z condition. And this will be equal to the car Z. I really should have copied these. And then the final condition is a little bit trickier. This uses something that we've not seen so far. Because this is our otherwise condition, so we now have a bunch of other conditions that we have to match against. We've only specified the behavior for 2 characters. We need to specify the behavior on all characters. So what I'm going to use is something in Haskell that's called a wildcard. Now this just means I don't care what the input is. It just means if it hasn't met any of the other conditions, then just do this one for all else. So this is kind of like your else or your otherwise statement. So that little underline just says whatever the input that goes in there is, I don't care what it is, just do this with it, as long as it's not the first 2. Car is not A or Z. And there we go. So these all have equivalent behavior in Haskell, and of course I can go in and I can colon L and pattern matching. I can load this in and I can do check car. Let's do check car on A, and I get the car as A. If I do this for 1, I'll get the car as A. If I do this for 2, of course I'll get the car as, oh, no actually I don't. Oh, is this because I've got a, right, okay, that's because I've got a capital H here. So we save that and we reload it, and then we can do this properly. Ooh. The car is A. It helps if you spell your function names properly. But yes, of course, these all have the same behavior because they're all the same function. These are just different methods for specifying them. So I want you to see that you will have many of these, the functions that you write in Haskell will have different solutions. So you can use guards, you can use ifs, you can use pattern matching. So your function might not be the same as your friend's function or your colleague's function or whatever it is, but it might have the same behavior. There will often be more than one way to approach things in Haskell. But I would very much recommend that you use these 2 over this. One of the joys of working with Haskell is that we get very clean, readable and concise code. You really don't want to be messing that up with a bunch of if statements if you don't need them. As I say, we'll be looking at I/O where it's much more reasonable to use if statements. But as it stands, I think these 2 are much cleaner, much easier to read, and to understand. Even if you haven't seen Haskell before, you get an idea of what they're doing just based on the code that's written there, whereas this is much, much, much harder to read. And of course, these two will scale much better than this will, so I would try and get used to using these functions, or these syntax methods in Haskell. So that's everything for today. Of course, if you have any questions about anything I've covered today, please do let me know. Thanks.